All right, so here we're going to introduce the concept of an eigenvalue, right? So what we want to do, right, we're studying what a matrix does to every vector. Now we're going to focus on a particular type of relationship, right? We're looking for special vectors that a matrix simply scales, right? So what I mean by that is, so mathematically, what we are after is looking for having some vector v and some vector x, some vector x and a matrix A, right? Are there values of lambda here where this relationship exists, right? Now, what this means, the way you interpret this, now remember when we have A is a matrix, X is a vector, but keep in mind if A is a square n by n matrix, that means that this column vector X is n by 1, right? These have to match up. So our resulting product is another column vector, right? N by 1. Okay, and then lambda, Greek letter lambda, is just some real valued scalar. Okay, so the idea here is that the matrix multiplication of AX is equal to lambda x, means that A doesn't change the direction of X, right? If our vector X is in this case, remember lambda is a scalar, right? So the only thing that lambda x does, it scales it, either if it's more than 1, right, we get this longer value here, lambda x. All right, it can also go in the negative value. Lambda x. Okay, so it stretches, shrinks it. All right, if it's smaller than 1, right, then it would be like somewhere here. Right, but all in all, it does not change the direction. All right, so these values are lambda, or what we call an eigenvalue, right? So an eigenvalue for a square matrix, if there exists a non-zero vector such that this is true, right? We're not always guaranteed for it to be true, but if it is true, it is an eigenvalue, all right? And the non-zero vector x is what we call our eigenvector of A for the eigenvalue. All right. Now, eigenvectors must be non-zero. All right. The zero vector satisfies the above equation for sure, but again, that is just the trivial solution. All right, and lambda could be any value, so we just excluded here for our definition. Right. So this will always be true, right, for all values of lambda. So again, right, just trivial solution. We don't care about it in terms of our eigenvalue, eigenvector situation here. We want the eigenvector to be a non-zero vector. All right. So the question over the next couple of videos here is, how do we find these eigenvalues? All right. So that's going to be what we're going to be focusing on, right? This idea of finding eigenvalues. Okay, so what we're after is we are looking for lambdas that satisfy this equation. So again, since it's an equation, what I'll do is, right, I'll do some arithmetic here, or some algebra. I'll bring the lambda x over to the other side. So A x minus lambda x. Again, just keeping in mind what operations I did. So when I subtract, I don't get 0, I get the 0 vector. Okay, right, because all these operations are valid, so I got to make sure what I place in there is valid in the sense of its place here in proper operations that are valid, right? Now, another thing here that we can do is we can factor on the right. Not on the left, A and lambda are, well, they're not equal, right? A is a matrix, lambda is a scalar, right? So what I'll do is I'll factor on the right, since I have x here. Now I do have to be careful how I treat this, right? The one on the left here, that's just a, that's fine, right? Minus, but remember this is lambda, and I need these operations to work out properly, right? So here, remember this needs to be n by n, because it's n by n here, right? So it's not lambda times 1. So we think of, in terms of matrices, what represents a 1? Well, the identity matrix, right? So here what we have is lambda in. Okay? All right, so when factoring this, remember in times x will give us the vector x back. Okay? So now we have something to work with, right? Now we have a homogeneous system. Okay? Now, homogeneous system has a non-trivial solution, again, as always, right? X equals 0 always works, but we're not interested in that solution here. Okay? So what we're interested here is in a non-trivial solution. Well, in terms of what I've been talking about with matrices, I know non-singular matrices give me only the trivial solution. So what I'm looking for here is that this matrix here is singular. Right, now again, that means a lot of things in terms of properties of the matrix, right? We defined it in that NME, I believe 7 we're at this round here, right? That can mean a lot of different things, right? If it's non-singular, its columns are linearly dependent, right? Has a trivial null space, etc. But in terms of what we learned recently when we're talking about determinants, well, what it means to be singular is that the determinant is 0. Okay, so that means that the determinant, in order for this to have a non-trivial solution, the determinant of this matrix is going to have to be 0, right? Not the 0 vector here, right? Determinant is, the value of it is a scalar, so it must equal to 0, the number 0. And this is exactly how we're going to find eigenvalues, right? By setting up an equation like this. All right, we have determinant minus the lambda times the identity matrix of n, and set that determinant equal to 0. So we're going to use, right, properties of determinants when needed, right, and being able to calculate determinants, right, as needed here as well. Okay, all right, and that's what we'll focus on in the next video. We'll see that what this is going to come down to is to finding roots of a polynomial.